So the last thing I wanted to discuss today was what is the interpretation of the wave function. So what does the wave function mean? So it's generally accepted that the wave function psi contains all the information that can be obtained about the state of a system. Now, because of this, psi is often called the state vector or just the state. Now, what is the operational meaning of this? The operational meaning of this is that if I take psi and take its complex conjugate, of course it's a function of space and also time, but let me just suppress the time dependence. Then psi star psi, which is a real quantity, this is a probability density. So this is known as the Born interpretation of the wave function. So what does this mean? Suppose that you want to know what is the, so you have some space-time and you have some point in space-time and you have a small region there and you want to know what is the probability of me finding the particle in this little region of space-time or space. Then the answer is, according to Born, is that the probability is going to be P of r, d cubed of r, is going to be given by psi star psi times d cubed of r, where d cubed of r is this volume. Okay, so this is the interpretation, probabilistic interpretation. So there are two important cases. Okay, case number one is that the state psi is normalizable. So essentially, physically, what it means is that somehow the particle is contained within some finite region of space. So what this means mathematically is that if I take the volume integral of the psi star psi, and it's some constant n, a real constant, of course, because this guy is real, then this is not infinity, it's less than infinity. So that is when we say psi is normalizable. What it means is that we can always define psi prime, a new wave, a wave function, which is related to the old one by like this, and then the normalization of psi star will be the same as psi. Well, psi star will be 1. So in a sense that psi and psi prime, they describe the same physics of the same system, but psi star, the probabilities have been normalized. But there's also the second case, which is also important, where psi is not normalizable. And this is an important case. For example, the case where we have a plane wave solution. It should be quite obvious that this is, if you integrate this over all space, this is not going to give you a finite number. So this is not normalizable. So in this case, we say that the interpretation of psi star psi has the interpretation as a probability density, but relative probability density. So it's not an absolute or normalizable probability density, it's a relative probability density. So, we can say, oh, if this is our space, and we divide it up into, bits and pieces, then it can tell us what is the relative probability of us finding the particle here and here. Okay? So these are the interpretation of the norm of the wave function. So because the wave function has an interpretation in terms of probability, it's important that once we normalize it, that normalization stays constant in time. Otherwise, the interpretation of it being a probability density will not have any meaning, because it'll just mean that, oh, just after a few moments we have to measure the wave function again in order to predict where the particles are, and that the Schrodinger equation is not going to describe the dynamics of a sensible physical system. So let's show that the normalization is actually preserved. So the normalization, let's call it n, and it's d cubed. So d cubed r psi star of psi. So here, I mean, the integral is a 3 integral. Actually, I'm going to use the 3 integral sign here. So then, let's look at the Schrodinger equation. So the Schrodinger equation is this. So previously, we took the time reversal of the Schrodinger equation and did a complex conjugate, but now we're just going to take the complex conjugate. Then I just get this thing. So now what I can do is that I can say, okay, I'm going to use these two guys in taking the time derivative of n. So I want to know what the time derivative of n is. Of course, this is going to be psi star psi. But of course, this thing is integrated over all space, so it doesn't depend on space anymore. So I can write the total time derivative as a partial time derivative. There's no harm in that. And my volume element is not changing. My limits are not changing with time. So I can just do the, a derivative onto the integral sign. And then what I do is that I use the Leibniz Rule. So if I use the Leibniz Rule, what I get is d psi star dt times psi plus psi star d psi by dt. And then here what we do is we use these guys, these two equations. And if I do that, then what I get is, for the first term, I get h bar divided by 2im times, I get the Laplacian psi star times psi. And for the second term, I get minus h by 2im psi star del squared of psi. And what happens is that these two terms, the potential terms, they cancel out. So we only get the derivative terms. So, and then, what we have here is we can factor out this thing. And then inside, what we have left is, okay, first we factor out the constants. But inside what we have left is the gradient of psi star times psi minus psi star, the gradient of psi. Of course, if I apply this guy onto this, I'll get two terms. So one would be del bar psi star, another one would be del psi. Well, one term would be del psi star, del psi. Another term would be del squared of psi and psi. So the del squared of psi is the term we have here, but the other term here will cancel with another term here, so we will have these two terms left over. That's pretty easy to see. But this thing has the form where we have a, so we have a volume integral, V, and we have divergence of some vector. And we know that Gauss's theorem tells us that divergence of that vector can be written as a surface integral over the boundary. So this means I don't know why. This is the boundary of V, and then it'll be a n dot V times dA, where n is the normal to the boundary of the volume. So if we have the volume V and these are the normals, so a three-dimensional volume integral, which has, where the integrand has the form of the divergence of something, can be written as a surface integral on the boundary where the vector is dotted with the normal vectors here. So this is the famous Gauss's divergence theorem, or it's also called Green's second theorem or something. So we can use this into our this guy, and what we find is that the dN by dt is going to be given by h bar by 2im, and the surface integral at infinity and of n dotted, so n is a vector, so let me use that, dotted with this vector, but remember that our volume was over all space. So the surface integral that we are doing here is on the boundary of space. So this is like a huge sphere that we are integrating over. And if our wave function psi is normalizable, as we're assuming, then it's going to go to zero, either like psi, and its gradient is going to go to zero as we approach the infinite regions of space. And that is where we are doing this integral. So the integrand is going to be zero. And therefore, the whole right-hand side is going to be zero. So as a consequence, we have that the normalization of the wave function will be preserved in time. And that allows for a good probabilistic interpretation of our wave function.